Welcome to today's High Energy and Mathematics seminar. Today, we are happy to have Carlos Arguelles talking about neutrino astronomy. Carlos is an assistant professor at Harvard University. He obtained his PhD at the University of Wisconsin-Madison and then became a postdoc at MIT, during which he have won many awards and fellowship, including International Union of Pure and Applied Physics Young Scientist Prize in Astroparticle Physics, Sloan Research Fellow, IceCube Collaboration Impact Award, and etc. It focuses on neutrino physics. Please raise your hand if you have any question during the talk. Thank you again for giving us this talk, Carlos, and would you please take the conference?
Thank you for the invitation, and I'm glad to be here to talk to you about Neutrino Astronomy. And I've called this Detectors, Techniques, and Status. And let me try to tell you what I'm trying to achieve here. And as Jesse said, if you have any questions, just raise your hand and we can chat. Since I think that this is a relatively small group of people. So what is the objective of this lecture series? So we have, well, today's 2 hours, is to try to understand how our universe looks in neutrino. We can see our universe in multiple ways, and so you can see illustration of that in these glass paintings. And so on the rightmost, you see the universe visioned in optical, ground-based and space-based observatories, as well as gamma rays, and in general light. In the middle one is how we see our universe in gravitational waves that are produced when, for example, two black holes merge. This is what's shown in this picture. What we're going to think about today is the leftmost figure, which is our universe in neutrinos. And this picture, these little circles in red and green and blue, will become clear once we talk about how neutrinos are detected and how we portray them in our event displays. And what's important to think about is that neutrinos given us complementary information about astrophysical objects, and in particular, they're going to tell us about hadronic production in these objects. So my underlying objective for this talk is twofold. So one of them is to empower you, is to let you be able to, at least first glance, go and use the actual data that's currently available in these fields. So for example, in IceCube, if you go to this URL down here, just go to the IceCube website, you can find these data releases that contain a lot of information and data that can be used probably for your own analysis. So what I wanted to do is give you the tools to be able to understand how to use this data so you can try to answer your own questions. And then my second objective is to update you and let you know what's the current status of this subfield. And I have 5 points that I would like to cover, which are why high neutrino astrophysics, why are we doing this very difficult endeavor? I want to tell you a little about the history of this field, how did we start it, and how we got to where we are. Then we'll talk about the signatures of neutrinos from outer space, the backgrounds that one faces in detecting those neutrinos, and the particle physics that's associated to understanding their signatures. Then I want to discuss how these neutrinos were discovered, what were the selections, what were the different criteria used to discover neutrinos, and then 5 is sort of the status of this field, which is what do we know about neutrino sources. I think that's probably all the time we will have, but if we do have time, we will talk about either next generation detectors or particle physics opportunities, which is most of what I work with is 6 and 7. So let me talk about why we're doing this. So the beginning of neutrino astronomy is actually predates high neutrino astrophysics and is associated to the observation of supernova in the large magnetic cloud, and this is supernova 97.8, and this was actually observed in neutrinos, as you can see here on the right, the neutrino observation of 3 neutrino detectors, Kamiokande, AMB in the US, and Baksan in Russia. But when we're talking about neutrino astronomy here in this talk, we are not talking about, I'm sorry, and these neutrinos are in the tens of MeV of energy range. But when we're talking about neutrino astronomy in this lecture, we're thinking about neutrinos that are very high energy. And these neutrinos are produced in the highest energy collisions. And so one of the oldest problems in particle astrophysics is the origin of cosmic rays. And so here in this figure on the left, you see the cosmic ray spectrum as a function of energy in electron volts. An electron volt is for reference, 1 gigaelectron volt or 10 to the 9 electron volts is the energy of a proton at rest approximately. And the vertical axis shows you the intensity of particles that arise at Earth. So you can see that the cosmic ray spectrum in energy spans more than 11 orders of magnitude, and then in intensity spans more than 30 orders of magnitude. And the question is, how is it at the highest energy of these particles, how is it that the universe is able to accelerate particles at such high energies? What are the mechanisms of acceleration? So the highest energy cosmic ray that we have observed was seen by the Fly Eye experiments in 1991, and it had 3 to the 9 TeVs. A TeV is 1,000 GeVs, and is close to the center of mass energy of the LHC at these scales. If you use conventional technologies, such as the ones that the Large Hadron Collider uses, which is center of mass energy of 14 TeVs, to produce such a high energy cosmic ray or particle, we will need to have an accelerator that's the orbit or circumference of Mercury. So this is very, very energetic particle. So I'm a particle physicist, so I'm going to tell you how I think these neutrinos and these particles are produced in outer space. So let me first tell you how we actually produce high energy neutrinos here at Earth. So we have some kind of accelerator. That accelerator accelerates protons to high energies through a combination of electric and magnetic fields. Then those high energy protons are dumped into a target. That target has some dense material, and in the collision of protons with this target, you produce unstable particles such as pions. These pions then decay, and if there is a magnetic field around this target, the charged particles are deflected. However, the neutral particles, such as neutrinos, are not deflected. So then the end product of this is a directional beam of neutrinos. So the analogous thing that happens in the universe is that there is some kind of cosmic accelerator that could be a supermassive black hole that through its gravitational forces is accelerating matter around it. That matter, protons, collides with nearby radiation or gas around the black hole. And in those collisions, then it produces, again, pions that decay into neutrinos and light. The most relevant relationships are going to be the ones shown here on the bottom right. And for example, a high energy proton, when it interacts with radiation around the black hole, produces a neutron and a charged pion, and the charged pion subsequently decays into a neutrino. And so what's able to exit this acceleration region is then the neutron, which could be a cosmic ray, could be a cosmic ray later, and neutrino. You could also have a production of neutral pions, which will produce high energy gamma rays. And so then it means that the production of neutrinos and the production of high energy gamma rays are correlated at their sources. So you could ask, well, you could just use the gamma rays to try to look for these accelerators. And the problem is that if you have a high energy accelerator as shown here, it's emitting gamma rays. In this illustration. When these high energy gamma rays, they interact with the CMB at above certain energy, and they can produce a pair of electrons. And so the universe at the highest energy is actually going to be opaque to light. You can also not see the charged particles that are able to leave the acceleration region. so high energy protons, because those charged particles are actually going to be deflected by the intergalactic magnetic fields and not reaches. So here enters neutrinos. And let me show this in a more quantitative fashion. So here in the horizontal axis is the energy of the messenger in electron volts. And remember that 10 to the 9 electron volts is the mass of proton in energy. And the vertical axis is the distance that we are looking at in megaparsecs. And so at the lowest at the lowest energies, we have a microwave light, and then you can go up in the light spectrum to high energy light as gamma rays in the GeV energy range. What's shown here in dark is where the high energy gamma rays interact with the CMB or ambient light present in the universe, and that makes the universe opaque to that light. That is going to be what we're going to be after, and it's the high energy, high distance behavior of the universe, and the terra incognita already revealed by neutrinos. And this is where these, I call them here dragons, where these very high energy accelerators live. So neutrinos, perhaps the perfect messenger, they're going to be they're electrically neutral, so they are not deflected by magnetic fields. They're massless, close to massless. We'll talk about it later. They are unabsorbed because they are interact through the weak process, and so they are not stopped by things in their path, or rather at the source. And then they're able to track nuclear processes. They're going to tell us how much harmonic activity is in these sources. And they may reveal, by looking at their directions, the sources of cosmic rays. The difficult part is that you need a very large detector to detect them, since they only interact weakly. So the question that follows is, how big of a detector do you need to see these high energy cosmic rays? And what I'm going to show you now is a calculation that was done, could have been done already in the late 60s. So here I show you different photon spectrum. This is the unified photon spectrum. So you can see that the most abundant light source is the CMB. And here I show you the highest energy cosmic rays. So those are our beam at this rightmost intensity. And when you have a high energy cosmic ray, it can interact with a CMB photon, as I was saying earlier. Sorry, every cosmic ray can interact with a CMB photon. And in that interaction, you can also produce a neutrino. So if I take the amount of cosmic rays and I take the amount of CMB, I can compute the neutrino emission that's produced by those high energy cosmic rays and those photons. And it turns out that high energy cosmic rays at the highest energies are going to interact with the CMB and disappear, producing neutrinos of energy similar to 10 to the 6 TeVs. And the intensity that you would require to see one neutrino is about 1 cubic kilometer. And so it's a large detector, but and there are very few, but now it points to its source. And so this was done by this was discussed in the 60s. And one thing that Markov, here have Markov Pontecorvo, proposed is that to build such a large detector, maybe you should install detectors in a deep lake or sea and look for the Cherenkov light of charged particles that produce neutrino interactions. And that way you could build such a large array. So now let me give you a little of history. So the first ideas to build such a large underground detector was the Dumont project, which was started in the early mid-70s and ended in the mid-90s. And this is one of the earliest cartoons of Dumont. Dumont is an interesting experience, even though Dumont itself never happened. Many of the concepts of neutrino astronomy were set up by Dumont. And so the idea was to have Dumont be underwater and be an array of sensors that will detect these high neutrinos. So here you have an illustration of demand. So this is an order cubic kilometer array. Like this magic cubic kilometer number comes from the intensity of ultra high energy cosmic rays interact with the CMB, as I was saying earlier. So they knew that already in the 70s. And the problem is, you don't have money to build that. So they started with this idea of having a 1 cubic kilometer array, which is 20,000 of these detection units in a grid. But they have started with thinking about smaller prototypes, as you can see in the sequence of arrays. And then in the end, they got to these small configurations. They end up deploying one configuration called triads, which I think had eventually 3 strings. And unfortunately, that had electronic problems when it was deployed on water, and then the project stopped. Even though that project stopped, from the Duman project, various projects speared out in different directions. This was in the middle of the Cold War, so Duman had both Russians and non-Russian collaborators. And so the Russians split onto their own path, and so they went and built an experiment in Lake Baikal. Lake Baikal is one of the deepest lakes in the world. And they actually were able to be the first ones to detect a neutrino produced in the atmosphere. This was done in 96, and you can see the event display here in the center. This is an upward going neutrino. So the vertical lines you can see here are the 4 lines that Duman had. The circles are each of their detection units, comprised of 2 PMTs in coincidence so that they could reject noise. And then you have this upward going trajectory that you can see here. Another group spread out in a different direction, and they led to the Amanda project. And so the Amanda tried to, instead of using water, use ice in the Antarctica to look for neutrino interactions. And so the idea was to drill holes in the Antarctic glacier and to put light sensors facing downwards to look for neutrino interactions. And this is shown here in the figure on the left. This is more or less the Amanda ray. And you can see that the Amanda ray was deployed about 1.5 kilometers to 2 kilometers deep in the ice. It turns out that the properties of the ice change quite dramatically as you go in depth. And the first version of Amanda 1, was deployed about 1.5 kilometers, a little less than a kilometer deep in the glacier. And it was unfortunately in the region where there was so much scattering that you couldn't resolve tracks correctly. The second version of Amanda was deployed deeper, where the scattering length is longer, so that the light is able to get to your detectors unscattered. Always left scattering. And you can see that here on this figure on the right, so the effective scattering coefficient, so the inverse of the scattering length, how that depends on the depth. And that's something that they discovered as they were going through this. And they also were able to observe atmospheric neutrinos. And so this figure on the top right is atmospheric neutrino seen by the Amanda 2 experiments. Another group of people branched in a different direction, and they went to the Mediterranean Sea, and that was Antares. And so Antares deployed also arrays in the bottom of the Mediterranean, a couple of kilometers deep. And this is, for example, one of their neutrino displays. And Antares actually operated all the way until, I believe, 2018, just before the pandemic. So that's all the history I'm going to tell you, but I think it's quite interesting to see how this field has evolved with times. There are a couple of resources if you're interested in neutrino history. I think one of the best reviews on these topics was written by Christian Spearing. This is called Towards High Neutrino Astronomy. It's a very enjoyable read. And if you're looking for books, one about IceCube that is very well done was with Mark Bowen. And then there is also Neutrino Hunters that has a history of neutrinos. And also there is the Neutrino History Conference, which is shown here in the bottom that you can find more information on this. Okay, so let me just now talk about IceCube and how it works and how it actually is able to seize neutrinos with more detectors. Though some of these concepts are portable to other experiments operating in water. So first of all, I should tell you that ice cube is in the Antarctic continent. Antarctic is actually quite a large place, and it's actually going to be located near the geographic South Pole in the Amundsen Scott base, in US base. If you were to go there, you will see this building. This is the Ice Cube Computer Center. It stores the computers for detectors. And then you see these sort of arms that are coming out of it. Those are going to be um, 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 structures to bring cables down into the ice to connect to the array. So what we do is we drill holes into the ice about 2 kilometers deep. So the holes are drilled first with first a weight to give initial direction of the hole. And then hot water drill is put in. This is the one that's shown here. And this shoots hot water at high pressure. And that's the one that actually makes the hole 2.5 kilometers deep. Somebody has a question. Oh, yeah, so the question is if I've been there. No, I haven't been there, but I hope to go there soon. So the ice cube array, this is an illustration of it. Antarctica, by the way, is a glacier, so there is rock below the glacier. At the geographic South Pole, it's about 2.5 kilometers tall. And the holes are 2.5 kilometers deep, and 1.5 kilometers into the hole is where the array starts being deployed. And you can see here the array is deployed between 1.5 kilometers and 2.5 kilometers. The holes are going to host these strings of detectors, and the strings are going to be separated horizontally about 125 meters and vertically about 17 meters. So why is it 125 meters and 70 meters? So this is these distance scales are optimized to improve neutrino directional reconstruction. The total amount of the total mass of neutrino of material that is encapsulated by this detector is about 1 gigaton of neutrinos of 1 gigaton of ice for neutrinos to interact. It's made out of these individual detection units. They're called data optical modules. When I was talking about the history of this field, all of these experiments use photomultiplier tubes, which are devices that convert light into currents. But all of the other prior designs to Ice Cube were called optical modules. The new thing about is this digital part. They are digital in that in prior designs, the photomultiplier signal was carried through the cable all the way to surface. What is new about the Ice Cube design, and this was a breakthrough when it was built about 20 years ago, is that the signal is digitalized in situ in the optical module in the board, and then a digital signal is sent out to the through the cable. And these digital optical modules or DOMs are arranged on a grid, as I was describing earlier. So let me talk to you a little about how neutrinos interact and what are we going to see here. So when we talk about the interactions of particles in high energy physics, we like to use Feynman diagrams. So for example, here is interaction between a neutrino and a d quark through exchange of a C boson. But neutrinos have another type of interaction that is makes the neutrino disappear. So for example, here the neutrino comes in, and what comes out is not a neutrino, but it's actually a charged particle. So electron neutrino comes in, and the electron comes out to the exchange of a charge mediator, in this case, the W boson. And in that interaction, the quark also changes identity. In the standard model, the neutrino and the charge particle that comes out of the neutrino interaction are intimately related, and they build into the structural standard model. And we're going to label the neutrinos by their so-called flavor, by the type of charge particle that they produce when they interact through this charge-current exchange. So an electron neutrino for us is going to be a neutrino that produces an electron when it interacts. A mu neutrino for us is going to be such that it produces a muon, and a tau neutrino produces a tau. Mu and taus being more heavy versions of the electrons. neutrino telescopes are actually are going to be able to see all of the different neutrino interaction types. So, for example, muon neutrinos producing these muons can be seen when they interact in the detectors or around it. Electron neutrinos are going to be able to be detected when they interact within the detector instrumented volume, and tau neutrinos can be noted when they interact inside. And so how is the interaction mechanism? How is the detection principle? So you have a neutrino that's coming in, say a mu neutrino comes in, it interacts in the iso rock around the detector, makes a Heinrich muons. Heinrich muons, and that is, as we'll see more detail in some slides, are able to go several kilometers in the iso rock. And then when the muon, Heinrich muon, is in ice, it will emit this Cherenkov radiation. By looking at the time and spatial position of the Cherenkov light, we can infer the direction of the muon. And because they are so high energies, the muon and the neutrino directions are going to be very collimated, and we can follow the neutrino direction. So these three Feynman diagrams I was showing you earlier, the mu-neutrino interaction, the electron-neutrino interactions, and tau-neutrino interactions are actually going to produce muons, electrons, and taus, which are going to then emit light in different ways within the array. And by looking at the way in which the light is deposited in the array, one can actually figure out the direction of or the type of particle. So for example, muons, they emit these long emissions of light, which we long call as tracks, for which the energy resolution is going to be poor, about a factor of 2, mostly because of the stochastic losses of the muon and the unknown interaction vertex, not necessarily contained within the detector volume. However, the long lever arm here is going to allow for good directional reconstruction, typically better than a degree at the super TV energies. Neutral current neutrino interactions or current electron neutrino interactions are going to make these hadronic electromagnetic cascades that are going to deposit light in an approximately isotropic way, making making these cascade-like features in the center. For those, we can measure the energy calorimetrically for 15% resolution, but the direction is not harder, about 10 degrees at hundreds of TeVs. We're also sensitive in an event by event basis to tau neutrinos for sufficiently high energy tau neutrinos. I'm sorry, in these figures, the little circles are each of the individual sensors, and the color indicates the time of arrival of light. So red is earlier time, and green and blue is later times. And so here you have a tau neutrino that's coming in, interacts in the red-blue blob, and then it's very boosted, and it disintegrates itself in the green blob. And this can be resolved when the energy of the tau is about hundreds of TeVs. And to give you a sense of scale, even though the tau lifetime is very short, a tau neutrino with a PeV of energy that's a million times a million GeVs goes approximately 50 meters on average. Okay, so how do we compute the number of detected events in this array? So suppose now that you have your detection volume, and this is shown as this blue box, and that's embedded in some material, rock, water, whatever. But my detector is in within this blue box, and it has some height L, so that's like a kilometer, okay? So I want to compute the number of neutrino interactions that happens within that volume in blue. So when an electron neutrino comes in, the electron neutrino has to enter my box L for me to see it, because the electron neutrinos produce these spherical light depositions that can be seen only when they're within the detector. If a muon neutrino comes in, it's a little more tricky, because a muon neutrino produces a high energy muon, and a high energy muon can go several kilometers before it loses a substantial amount of energy. And so that means that a muon neutrino, if it interacts inside, I will see it, but if it interacts outside, I can also see it, as long as the muon reaches my detector. And then the same for the tau. So the tau, as long as it's boosted enough, if the tau neutrino interacts outside, If the tau is boosted enough, I can also see it. So the region where the neutrino is able to, I'm able to see a neutrino event is actually going to be flavor dependent. The neutrino, electron neutrinos being the smaller region and the other neutrinos with the lighter regions. So what I'm going to do right now is focus mostly mu neutrinos. Oops. So the first thing that you have to do is you have to have the neutrino get from cross the Earth get to your detector. The Earth is in this figure, I guess, below us. Center of the Earth is below us in this figure. This may sound a little strange because neutrinos are really interacting particles, so we typically think that they just go through everything. However, when you have ultra high energy neutrinos, they do not necessarily are able to go through the whole planet. And so we need to account for the fact that not all of the neutrinos are going to make it through the Earth. So that's the neutrino survival probability. Then once the neutrino gets to our detector, then we need to account for the probability that the neutrino interacts within the relevant region. And that is going to be given, where here lambda is the neutrino interaction length, is 1 minus the exponential of minus L to X interaction length, or in the limit of small detector length to neutrino interaction length, about L over lambda nu. So the detectors typically here are going to be kilometers, and the interaction lengths are going to be typically still on the orders of hundreds of kilometers. Hundreds of kilometers is still long, but it still can be much shorter than the size of the planet, which is 10,000 kilometers. So for the length, well, if it's an electron neutrino, the length that's relevant, this L, is the size of my detector, L, so I decide that. But for mu neutrinos, the length is going to be the range of the muon, which is going to depend on the neutrino energy, or the length of the tau, which is going to be a little simpler. We'll see why that is, but that is going to be given by that equation there. Then the probability to detect the neutrino is just going to be the neutrino cross sections times number of targets times this length. So let me start thinking about the neutrino interaction probability. It's the first element we need for this puzzle. So the neutrino cross section grows with energy. So here you have the neutrino energy in electron volts. The cross section is millibars. So you can see that at the low energies, the neutrino cross section grows linearly. Grows quadratically, then linearly. And what's going to matter for us is what happens with the neutrino cross sections at the highest energies in the TV energy range. So at the highest energies, the neutrino interaction is described by the so-called deep inelastic scattering, where the neutrino exchanges a W boson that interacts with the quarks in the nucleus. So here is a diagram of the neutrino nucleon scattering, where the neutrino has some form momenta K, it comes form momenta K2, and then the quark, the W boson has momentum transfer Q, which is the difference of this form momentum. So that's going to interact with a quark that's going to have a fraction of the form momenta of the proton X. So here are some measurements of the neutrino cross-section here shown divided by the neutrino energy. And so in the hundreds of GeV, and this will be true up to about maybe 100 GeVs or so, that the neutrino cross-section is approximately linearly with energy, and then it will have a little different energy dependence. And the neutrino cross-section is going to depend on the so-called structure functions. These are F1, F2, and F3, which are going to describe the distribution of quarks within the nucleus. So here I show you some more recent calculations of these cross-sections. So the charge current, neutral current cross-sections are shown at the top. And you can see their energy dependence. More importantly is their error. So in the region of TeV neutrinos, the neutrino nuclear cross-section is thought to be understood at the 4% level. And we're talking about neutrino nucleon scattering. There is some subtleties because we are not really scattering neutrinos with proton or neutrino with like neutron. We're scattering neutrinos with like oxygen or maybe with like iron in the earth. And those nuclear effects can make this there's a little larger, but in no case more than 10%. So the cross-section is understood at that level. You can also produce a W production, and this is known as the Glashow resonance. So you have an electron and neutrino can come in, and it can interact with an atomic electron, makes an on-shell W that then makes it into a QQ bar, and you can see that. That actually is most of the time an irrelevant process, except when you produce the W on shell. And in that happens when the energy of your antineutrino is about 6 PeVs. And you can see that in this figure here. So the lines that are in green and black are the neutrino nucleon scattering. As you can see, they're always the dominant neutrino interaction process, except for that moment when there is this red spike that goes above them. And that's when you have this W production. So for most of our discussions, we always be thinking about neutrino nucleon scattering, but neutrino electron scattering is relevant in that particular window. Okay, so what about how the neutrino interaction depends on flavor? So at the lowest energies, so below a TeV, the neutrino interaction, sorry, the neutrino cross-section has strong flavor dependence. The electron and mu neutrino cross-sections, they're very similar. However, the tau neutrino cross-section is smaller, and at 100 GeVs, about 10% smaller. However, as the energy increases, the cross-sections start becoming more and more similar. As you can see in this figure, they sort of start converging. And at the tens of TeV energies, which is what we're talking about, the cross-sections are going to be very, very similar. So this is a problem for low energy neutrino experiment, but for us, the neutrinos cross-section flavor independent. Okay. And so if you, I will use a cheat in a second, but another thing that's important is the inelasticity. The inelasticity tells you how much energy goes into the outgoing lepton. So an interaction that is more elastic means that the lepton that's produced from the neutrino interaction is more energetic, whereas an interaction that's more inelastic is that where the hadronic part is more energetic. And so when the elasticity is the fraction of energy that goes into the hadronic shower. So when Y, the building elasticity is very large, most of the energy is going to the hadron, and when Y is very small, most of the energy is going to the lepton. And so the mean elasticity changes with energies. And so in the TeV energy range, it depends from neutrinos and neutrinos, but it's between 0.3 and 0.5. And then at the highest energies, the difference disappears, and this is because the neutrinos interact predominantly with C quarks at high energies, which are symmetric between quarks and antiquarks, making the cross sections the same. Within elasticity, in any case, the tendency is for the neutrino interaction to become more inelastic with energy, which means most of the energy is going to the lepton. So this is what I wanted to give you as if you ever need to compute this in a simplest way, is to remember that the neutrino cross-section at high energies scales approximately like the energy to 0.36. And that the ratio of the charge current to neutral current cross-section is about 0.4. So the neutral current is about 40% of the charge current cross-section. These approximations are fairly good. And this together with the fact that the energy that goes into the lepton that comes out is about, depending if it's neutrino or antineutrino, 40% or 50%, depending on the energy range. With that, you can do a first estimation of what an interaction is. So this is pretty handy equations. Okay, now let's talk about the neutrino surviving from its air crossing in the endeavor. So here I show you in the vertical axis the neutrino interaction length in centimeter water equivalent as a function of the neutrino energy in GeVs. Okay, so at the lowest energies, the neutrino interaction length is very long, and then as it increases, and then the interactions becomes shorter and shorter. And what matters for us is the solid line, which is the total interaction length. Don't worry about the other lines. And then the red line I have drawn here is the diameter of the Earth in centimeter water equivalent. It's just a measure. Centimeter water equivalent is a measure of column depth. And so what you can see here is that somewhere around 10-ish of TeVs, so 10 to the 4 and a few, the interaction of the neutrino and the amount of material that the neutrino traverses becomes compatible. So below 40 TeVs, the Earth is transparent to neutrinos, but above it, the Earth becomes, in parts of the directions, becomes transparent to neutrinos. And that's actually going to be a direction-dependent statement. So you see here the field on the right, I have the Earth shown as these shells. There's the core of the Earth, which is denser, then the mantle, and then the outer crust. And I have ice cube here in the bottom. And I'm going to define the zenith angle as the angle with respect to the South Pole. So when the zenith angle is large, that means Earth core growing trajectories. For those trajectories, the column density is quite large. And in that case, the neutrinos are not able to go through the Earth if they have high enough energies. But if the angle is more shallow, then it could depend. So the absorption is an angular dependent property. Depends how much material you're actually going through. Okay, and this is the same plot for antineutrinos, but they're very similar. So we can think about the average Earth transparency, and that's known as the shadow factor. So if I average the absorption of the planets in neutrinos from any direction that is Earth through going, that's my shadow factor, so the average absorption. And so you can see here, this is a function of energy in GeVs. And so a shadow factor of 1 means that if I have an isotropic neutrino flux, it just gets to me isotropically. And shadow factor less than 1 means that part of my flux that goes through the core of the planet is getting absorbed and is disappearing. And so the shadow factor it starts being on the order of 10% only at the highest energies. This is a combination of the solid angle subtended. Here in my little diamond on the right, the core of the Earth looks too large. In reality, the solid angle substance is quite small. Okay. So when you're trying to compute, the flux that gets to your detector, when we're doing it is, if you care only about direction average neutrino arrival, you can just take your flux and multiply by the shadow factor, and that will give you the average in all directions flux that arrives at Earth. Okay. But in reality, of course, the Earth absorption is direction dependent. So you can see this here in the figure on the left. As a function of this same zenith angle, remember that zenith cos theta of 0 is horizontal coming neutrinos. Cos theta of 1 means core crossing neutrinos. And so you can see how as a function of energies, you have different Earth absorption. So at 10 TeVs is pretty shallow, but when you get to like 1,000 TeVs, which is a PV, it starts pretty steep, and 6 TeVs is even steeper. And then you can also see in the field on the left that there are certain features here, like around cos theta of more or less 0.85, 0.84. You see this kink. That kink corresponds to the mantle-core transition. And you can see other features here. And those are just going to correspond to different parts of the Earth, which I show you here on the right. So this is the preliminary air density model, which has different air layers. And so show you more or less the errors on those. So that in the percent ranges. So you could actually think about if we could measure the mass of the Earth by using this effect, because since the neutrinos are going to be affected in a direction-dependent way, they're sort of tomographically scanning the planet. If you could do this to measure the planet mass. And so the answer is yes. And so this was done with 1 year of ice cube data. And so you can see this on the figures on the right. If you look at, this is the number of neutrinos observed with respect to having been no Earth. And you can see how for air crossing trajectories, so which is negative cosine in this image, you can have there's less events detected. And this was done by this collaborator using ASCII public data. And they're actually able to measure the mass of the planets through weak force. And the measurement is shown here compared to the mass of the planet measured to gravitational forces. And I think it's really cool. And actually, one of my students is actually doing a new analysis that's going to update this with more data to be able to more precisely measure the mass of the planet with weak forces. And this is what we expect to do in terms of our next generation analysis. So here, the horizontal axis is the radius of the Earth, inner centered outer layers, and the larger bluer bars are the 1 year analysis, and this red is more or less what we think we can do right now, and we are working on that analysis, and we hope to present results in the summer conferences this year. Okay, so that's what about the survival probability of neutrinos. So most neutrinos, in most directions, neutrinos are going to get to the detector, but if your neutrino is coming through the core and it's high energy, it may not make it through. Now, once the neutrino gets to your detector, you produce these leptons and then they go certain distance. So let's talk about this distance L. So when you produce a muon, the muon is going to start losing energy. And at the highest energies, it's going to lose energy and preliminarily through 3 processes. It's going to Bremsstrahlung, pre-produce, and have photonuclear interactions. So the energy loss per unit column density, dEdx, where x is the amount of column density that the muon is going through, is going to be the sum of the different energy loss processes, ionization, Bremsstrahlung, pre-production, and photonuclear effects. It turns out that the ionization is approximately energy-independent energy loss. However, the other 3 processes, Bremsstrahlung, pre-production, and photonuclear energy losses, are actually proportional to the muon energy, to first order, with some dependence on the energy, but to first order proportional to the muon energy. So you can write the energy loss of the muon as minus dEdx is equal to some term that's ionization, which is approximately energy independent, not quite, but approximately. And then some constant that is approximately energy independent times n factor of E. And so in the approximation that A and B are energy independent exactly, you can solve for the distance that a muon can go through before it loses most of its energy. And that is given by this solution here, which depends then on the log of the muon energy. And it's going to depend on the energy loss coefficients, which are going to be material dependence. So for ice, these coefficients are given by those terms over here. So what does that mean? So here I show you the energy loss. So this is this dx as a function of energy. And so you can see this black line with green and blue just below it. Those are pre-production of Bremsstrahlung and photonuclear effects. So pre-production is the highest energy loss process for muons, followed closely by Bremsstrahlung and later photonuclear processes. And somewhere around the TeV, those are going to be the dominant energy losses. And below TeV, it's going to be ionization dominated. Okay. So now I can think about putting everything together. So the number of events is going to be my neutrino area times my neutrinos coming to this area. So the neutrino effective area is going to be the muon effective area times the probability of converting a neutrino to a muon times the number of neutrinos gets to my detector. The probability to convert neutrino to a muon is going to be the ratio of the neutrino interaction length to the muon range that we have discussed earlier. That's given the prior slide, that X. And so that's going to be the range of the muons times the number of that number of density of the neutrino cross section. And the convenient fact is that that's about 10 to the minus 6 at a TeV, and it scales linearly with energy to first order. Okay, so that's the conversion probability from neutrino to muon. And so then the effective area is going to be your geometrical muon acceptance area times your probability of survival of neutrino from Earth to detector times this conversion probability of neutrino to muon. So you can put everything together and it looks like this. So the effective area is linear or grows like e to the 2.2 below a TeV, like that. And this growth is a combination of the fact that the neutrino cross-section is growing linearly and the muon range is also growing. And so they're both growing with energy. At the higher energies, the neutrino cross-section starts growing slower, and the muon energy still has a logarithmic behavior, but then you have this change in slope is mostly for the neutrino cross-section. And if you want to compute the number of fan events in the neutrino telescopes, you are given this effective area, and then you can multiply by this by your incoming neutrino flux. And this effective area typically already accounts for Earth absorption when given. Okay, so how big is this effective area? So the effective area is energy dependent, but for example, at 100 TeV, all their first generation neutrino telescopes, such as Amanda and Antares, have an effective area of a few square meters. And if you another way to think about the effective area is that the effective area is the area that I will have such that if a neutrino goes through that area equivalent, it has 100% chances of making an event in my detector. Okay, so that's a way of interpreting this quantity. Whereas IceCube, with its 86 strings, is about 100 square meters. So it's about more than 20 times larger telescope than the prior generation. Okay, so the effective area is what's going to really tell you the area of your neutrino telescope. So when we say cubic kilometers or half a cubic kilometer or whatnot, that's not the relevant quantity. Relevant quantity is this effective area, which is a combination of the geometrical area and the neutrino interaction probability and its survival through the planets. So a 10 meter, at 100 square meter, is like has the same, it's comparable to a 10-meter gamma ray telescope. And so the Whipple telescope, gamma ray telescope operated in the 70s, was the first telescope to observe diffuse gamma ray emissions. And so it's not surprising that IceCube, which is similar in size, is able to see the first neutrino sources. Okay, so that's the comparison between gamma ray, comparison between what gamma ray astronomy is and what neutrino astronomy is. So gamma ray astronomy is ahead of us by about 50 years. So how do these effective areas look for real neutrino telescopes? Again, you can estimate this, but there are little details, exact geometries and efficiencies that will change this calculation. But you can see them here. And so the vertical axis is effective area in meters squared. The horizontal axis is the energy of the neutrino in GeV. And you can see that they are given in terms of various flavors and channels. So for example, if I want, says mu northern hemisphere tracks, that means I want muons. Tracks means muons. I want muons that are coming from the north. That if I want those type of neutrinos, the effective area will be this dashed black line. So if I want to compute the number of events, I will multiply the neutrino flux that I have from mu neutrinos with that area, and I integrate that in energy and multiply by time. Then you can also have the combined cascade channels. This is neutral current and charge current for the appropriate flavors. That's the black line here. And you can see now that if I want cascades, I'm also considering the W production. So that's why there's a spike there at in the glass resonance center here. Okay. Here I can show you something also that's interesting. So I was saying the effective area also takes into account the fact that the Earth is non-transparent at certain energies. So you can see here that the effective area is growing for most of these colorful lines. However, for this orange, which has a declination that is Earth core to going, is going downwards. That is just the effect of the Earth not being transparent. So the effective area encapsulates all of the relevant quantities. Okay, so let's proceed for at least a couple of minutes. I'm just going to get a glass of water and we will start in 1 or 2 minutes. Just give me 1 second for the little pause. Okay, so that's how we can compute the number of neutrino events. So let me talk about how do you go about inferring the properties of these events. And again, don't hesitate to ask questions as we go through. So when you have a high energy particle going faster than the speed of light in the medium, it produces Cherenkov emits Cherenkov light, and this Cherenkov light is emitted a particular shape. So on the right you have the Cherenkov cone, which occurs only when the particle is going faster than the speed of light. You can see how these cones superpose each other. And the Cherenkov angle is going to be dependent on the density of the material, on the index of refraction of the material. And for ice, that's going to produce an angle of about 41 degrees. And so this effect is essentially what this dog is doing. When you're moving faster than the speed of your medium, you're making this front, which is what we do but with light. And actually, if you look pretty closely at the ice cube logo, you will notice that there is this cone. This cone is actually drawn at the Cherenkov angle. So let me show you how this looks in an animation. So you have here the ice cube array shown as these dots in the background. And then you have a particle coming in, emitting these Cherenkov photons. And the Cherenkov photons travel through the ice and then hit the detector, right? Let's look at it once more. So it comes in the particles, the muon, muons emitting this Cherenkov light. And then you're seeing these sensors get hit. Here, the size of the spheres, by the way, is giving you an information about the light observed, and the color again means time. So what you can do to reconstruct the direction of the particle is look at the time of arrival of the photons and the location of arrival. So here, what I show you is the time of arrival in nanosecond with respect to some initial observed photon observation, and the vertical axis is the location of my photodetectors. So they're in a grid. So you can see that the photons have this exact cone-like shape when they are on time. So these are so-called direct photons. So by looking at the photon arrival time, we can reconstruct this sort of V shape, and from then infer the direction of the track. We should know that, remember that the processes of energy loss are stochastic in nature. And so what's that going to imply for this reconstruction? So the stochasticity is actually going to depend on energy. So what I show here is the distribution of final energy of various initial of high energy muons, going to two different amounts of material. So here is I have a 1 TeV muon if it goes 50 meters and if it goes 500 meters. So you can see that the distribution of losses is very broad. And that means that the energy reconstruction is always going to be dominated by this, by the fact that the energy losses are very highly stochastic process. So this is one of these muon tracks, but now compared to a person. Well, not quite a person, but here's 10 centimeter, 1 centimeter. So yeah, I guess it's compared to a person. This is for a 100 GeV track. So this is a 1 TeV track. So you can see how now you have these stochastic losses. So you can, on the left, you cannot see them. On the right, you see this production of little showers that are around the track. So the higher the energy of the track, It's 100 GeVs. This is a TeV. You can see that there is more stochastic energy losses going on. This is a higher energy track. Now this is a 10 TeV track. You can see this track had multiple higher stochastic losses, and when you zoom into those, you can see that those losses are significant. So let's look how those look in a realistic simulation. So here I have higher immune that's going through the eyes. This is the slide shown here. Oops. The color again means time, and each lines here is an individual photon that's been produced in the immune tract. So you can see here that when the interaction of the when the light is initially emitted by this at the beginning, it has this V-shaped cone at the very tip of the track, but then after that, the photons are diffuminating themselves as they travel. And just to remind you that the distance horizontally between each of these tracks is about 125 meters. So these photons are going several city blocks before they are absorbed. Okay, so this is a very to unfold then or infer the direction of the muon, you have to undo this energy loss process. So the absorption and scattering length is going to be medium dependent. So what I showed you before was ice, which has a smaller scattering length than absorption length. And this is what happens in water. So water has longer scattering length than absorption length, which means that in water, light is mostly unscattered and just goes in straight lines. And what that implies for you experimentally is that water-based detectors typically are able to reconstruct the direction of the muons better than ice-based detectors. However, light in water-based detector tends to be absorbed more, so you have less light compared to the ice case. So it's an issue of precision versus just more photons. So this is a very difficult problem because it's another simulation, because the photons that are detected are affected significantly by the scattering process that you see in the line. So here what you see is another one of these high energy muons going through, having multiple stochastic losses, and the little circles are the photomultipliers detected. And you can see sometimes they're really far away from the track. How to use those in an effective way is going to depend on your understanding of the ice properties. Okay. So go ahead.
Someone asked a question like he would like to know what programming language is being performed because it's a simulation, right?
Yeah. So these simulations are really expensive because there are so many photons that are produced. So this is being done run actually on GPUs using a language called CUDA. And in fact, we work very closely with NVIDIA to try to optimize the simulation of photons. Photon simulation, sometimes known as ray tracing, sorry, is something that's not only interest for us in neutrino physics when we make these sort of animations, but for example, when you're making like videos or video games, you need to also figure out where light is going to hit your characters, and those are also used in GPUs. So it's mostly GPU programming in C++ or CUDA, but this is actually very, very computationally expensive. So the reconstruction is an incomplete information problem, and I hope that answers your question. If not, please let me know. Okay, so it's an incomplete information challenge. So you have some photons, and then you have these detected particles, and what you have to do is figure out how was the light emitted. So for that, we usually use some likelihood-based reconstruction, though these days we also use machine learning technique. Oops. So here I show you the capacity of a neutrino telescope to reconstruct direction. So here the vertical axis is the median angle between the reconstructed direction and then the muon. And so ice-based detectors are shown here in colors, and black is a water-based detector. So you can see that the water, lower is better, more accuracy. So typically you can get at the highest energy is about 0.4 degrees angular resolution on average. There is a limit to how good you can do it. The kinematic angle between the muon and the neutrino on average is about 0.7 degrees at a TeV. So we are still not quite there, but in some cases we're getting close to that kinematic angle. In particular, in water, it's getting close. So the energy losses, how are they reconstructed? So the highest energies, the energy loss of a muon is actually proportional to the muon momenta, as shown in the figure on the top left. So what you can do is look at the energy losses along the track. Here, this is one of these high energy muons, and try to figure out the muon, how to estimate the rate of energy loss, and from that you can estimate the muon energy. So this is how these estimations can be are currently right now. So the horizontal axis is again the muon energy when it enters the detector, and the vertical axis is the error in the logarithmic of the energy. And so it's so bad that we don't talk about percentages; we talk about log of errors. And the reason that this is so bad is because of the fact that the muon losses are stochastic, because you're relying on the energy loss rate to tell you the muon energy, because the energy loss rate is a random process that introduces an intrinsic large variation in the energy reconstruction. So typically, muon energy reconstructions is going to be order one error, one energy. Okay, so let me talk a little bit about cascades. So this shows you three different cascades of different energies. So compared to a human size, so 10 GeV, 100 GeV, and TeV cascades. This is the longitudinal profile, and this is how you can differentiate between electromagnetic hadronic cascades. In the case of neutrino interactions, you're always going to have a hadronic cascade and sometimes an electromagnetic cascade if there's an electron producing an electron neutrino producing the interactions. Though you should remember that for the case of ice cube, the separation between sensors is in the smallest, more densely packed region is going to be about 70 meters. So all of this looks to us very much like point-like emission. So let me show you how this looks in picture. So this is a 1 TeV cascade in ice. So it starts emitting the light, and so you can see how the light scatters and has this hair-like sort of behavior. And so the light becomes late light here in blue, and then eventually it will hit some of your sensors, and you can try to infer the original emission points. In water, as I was saying earlier, water tends to scatter things less than ice, and so light just goes is emitted more directly, as you can see here. So there's less of this diffusion process is happening much less. And it's actually good because it allows you to more effectively reconstruct the position of these laws. So here I show an example of how this is actually done. This is a real data event of Ice Cube. The event is from the center, and then there are these panels around it. So I want you to pay attention to these panels. And so I show you lines in blue and in red and the data points. So every little square shows you the number of photons detected in a photomultiplier as a function of time. Okay, so this is how many hits were observed as a function of time. You see here the two different reconstructions. The most likely direction is this blue arrow. It's kind of hard to see in this image, but it's going to the right, and then the incorrect reconstruction would be going to the left and right. So even though a cascade looks like a blob, the light is emitted in an asymmetric fashion, and that asymmetry remains in the way the light is deposited. So we can use the details of the light arrival times of the light to be able to infer the direction of these tracks. Okay, so suppose that you want to do it all by yourself, trying to reconstruct these particles, simulate these events. How do I do it? So we have this open source solution to this problem. It's called Prometheus. So it's an open source neutrino telescope simulation. It does the particle injection, it puts in the cross section for you, it propagates these particles and it simulates the light yield. You usually need a GPU for that part. And plus, whereas propagating the photons, which is a GPU intensive component, sorry. And you can find that in this GitHub, in our group's GitHub, it's called Prometheus, and there's a paper associated to it that you can really follow these details. And then you can just go and all of these videos I was showing you and these things, you can just do it yourself and try it out. And one thing that's cool about Prometheus is that you can actually design your own neutrino telescope. So here we show you some examples of current neutrino telescopes that we have. IceCube exists, and IceCube Gen 2 is next generation IceCube detector. These are other designs: ARCA in the Mediterranean, ORCA in the Mediterranean, P1 in Canada, GVD in Russia. Trident is a proposed experiment in China. As you can see, it's very large. But you can just put any point you want to design your detector in a different way, move your strings around, you can do it in Prometheus, and you can do your own simulations, and you get these very cool displays. Yeah. Okay, so I hope that's useful for you all. It's very computationally expensive, and this is related to the question earlier. Most of the time is spent in simulating photons, so you can see here the execution time of simulated neutrino interactions, and so it's a stack histogram. So most of the time is in this pink color, which is just tracking all of these photons. There's just so much light produced. If you use our simulation, you can just compute this effective file, as I was telling you about earlier. You could do this with pen and paper, but you could just do it with the computer. And here we show you how Prometheus simulation reproduces different experiments results, and it does a pretty good job. Experimental results, by official experimental results, are shown in these shaded regions, and our open source simulations are these lines, and it's actually pretty good. Okay, let me talk about how am I doing time? Let me talk about backgrounds briefly. I will just be brief here. But there's lots of muons that are seen in IceCube that are not made of neutrinos. They're about 1 every 3,000 seconds, so 3 kilohertz background rate, making about 10 to the 11 muons per year. About 1 every 6 minutes, one of these muons will actually be made by a neutrino producing an atmosphere, making 100,000 atmospheric neutrinos per year. And we're trying to find 100 cosmic neutrinos, right? So this is like a 10 to the 9 background rejection you have to do. So where are these coming from? Well, they're coming from the collision of cosmic rays in the Earth with the atmosphere, making high energy particles in the case of mesons. Since I'm a little late, I'm going to skip to what I want to say, which is this. So the muons are produced mostly from the decay of pions. As you can see here, the muon intensity is a function of energy, and then the neutrino intensity is a function of energy. So what's curious is the muons are produced mostly from the decay of pions, but the neutrinos are produced mostly from the decay of kaons at the highest energies, and that's due to a kinematic effect. You can also produce electroneutrinos in these atmospheric showers, and those going to be slightly smaller contributions, primarily produced by kaons in the TVN range, and later on by these. And so this is maybe the most dramatic figure. So here you show the number of data events as a function of the direction. So when we're looking at neutrino particles that are going downwards, you are just flooded by all of these downward going muons. Downward going muons are not able to cross the planet, so they are not going to cover the whole sky, but they're going to be a very large background in this so-called downgoing direction. Downgoing means that if you were to stand in the South Pole, they are coming down at you in this notation. So atmospheric neutrinos are still going to be a background, and they're going to be in this more or less horizontal rate. And what we're looking for is something even smaller than atmospheric neutrinos. So how do we find these astrophysical neutrinos? So it's difficult because the flux is very small and the backgrounds are very large. And so here in the figure on the right, I show you the intensity of neutrinos scaled by energy squared as a function of the log of the neutrino energy. And these lines that you see here are so-called conventional. They are atmospheric neutrino calculations and measurements. And so those are the backgrounds. And the green bar that you see there, that's my signal. So I have to low, very, very low to see my signal. And this doesn't even take into account that for every neutrino that I see a million muons. So I need to overcome these very large backgrounds. And so the first thing you could do is, well, most of your background is in this right side of this figure, these atmospheric muons. So why don't we look in the easier parts where the atmospheric neutrinos are much less on a rate of about 2 millihertz. So strategy number one is the following. Instead of looking at all directions, let's just look through the planet, because through the planet, only neutrinos are able to go through. And you can do that. And so here is how did we saw atmospheric artificial neutrinos in that way. Here is the energy of the muon in the horizontal axis, and the vertical axis is the rate of events. And you can see the data is coming down as a function of energy. And we actually understand fairly well how atmospheric neutrinos are diminishing as energy increases, because those are produced by cosmic rays, which we measure and model. So the red line that you see here is the prediction of atmospheric neutrinos falling down with energy. And you can see that somewhere around maybe 20 or 30 TeVs, their data is above the red line. And that's because a new component of neutrinos is contributing to the neutrino detection, and that's astrophysical neutrinos. So essentially what you do is you look for neutrinos in the Earth crossing direction, and then you look at the highest part, and then you see an excess over the expected number of atmospheric neutrino events. So this has actually been done now. That was the original analysis, and then it has been done now with more years of data. And so you can see here, in every year of data that we do it, there's always an excess over this expected blue histogram. And that corresponds to an astrophysical neutrino, which you can characterize as a power law, which is a relatively hard index. And this measurement at the time gives you a 2.19, 2.2 spectral index. The other possibility is, like, the problem is all of these muons, why don't we select, why don't we try to throw them out by rejecting all events that interact in the outer parts of my detector? So in this case, you define an outer veto region, and you select only events that interact within the instrumented volume, and shown in these figures here. And so if you do that, the advantage is that you can now see all directions. And that's important because the galaxy for IceCube is in the southern hemisphere. So this is known as the high energy starting events. We call them starting events because they start within the detector instrumented volume and it's high energy. Wait, somebody saying something on the chat. Let's see. Also, the question is, why is the uncertainty so large at the tail? Let's go back to that other slide. Oops. Yes. So you mean the data error bars?
Yes.
Yeah, it's a statistical in these error bars here, statistical in nature, and it's just because at the highest energies, you have very few events. Right now, above maybe 60 TeVs, we have order hundreds of events. So when you bin them, they have large statistical errors. This is a log scale plot. So there's so many events in the other bins that their statistical errors are actually smaller than the size of these dots. So it's a statistically dominated problem. Big GGC. So the other option is to look for neutrinos that interact with the detector instrumented volume. And so what you do is you can look at the energy of your event, how much energy it deposited in the outer regions, and how much energy deposited in the entire detector. And we can measure this energy to the charge that it deposited. So here in this three-dimensional histogram, the rightmost histogram is the charge in the outer layer, and the left axis is the charge of the entire event, and the vertical axis is just counts. And so you can see that there is this falling background. There's lots of things that emit that have high charge, but they also have high charge in the outer layer. But if I select events that have less than 3 photoelectrons in the outer layer, so very little charge in the outer layer, I see that there is this line of events in yellow that is sticking out. These are different events. These are astrophysical neutrino events. And these actually are some of the highest energy neutrinos we've ever observed. The first ones, we named them by these mapped characters. And so these are some of the three highest energy neutrinos we've seen: Bird, Ernie, and Big Bird, with a PeV, 1.1 PeV, and 2 PeV of energy. You know, if you look at long enough, they kind of look like they're mapped characters, but maybe it's, you know, we're looking at them way too long. And there's another way which we can see astrophysical neutrinos, by the way, and it's the fact that something that I didn't tell you is that IceCube also has a top subarray of which cosmic ray detectors. And so this is an example, for example, this is an example of an event that is downward going, but it goes through the isotope array, you know, in a time where there is no hits. This allows us to know that many of these events have to be astrophysical in nature. So when you look at the high energy events, they look like this. So the horizontal axis is the energy deposited in TeV, and the vertical axis is the directions. And we know many of these starting events are actually astrophysical neutrinos, and we know this because of the angular distribution of these events. So the angular distribution is going to allow us to separate astrophysical and non-astrophysical events. How do we do that? Well, here in the figure on the left, I show you the angular distribution of different components of neutrinos as a function of for a given energy. So you can see that the astrophysical components, here shown in black, is kind of flat with it goes down at quarter one directions, but it's kind of flattish. Whereas there is two backgrounds which are spiky at cos theta equals 0, and there's another background which is this prompt, which is charm-produced neutrinos, which is also flattish. So one thing that we can take into account is that when a neutrino is produced in the atmosphere, it's produced in correlation with a cosmic ray air shower. So by selecting events that interact within the instrumented volume and do not have any incoming charge outside, we select events that cannot be produced by cosmic ray air showers. And what that does, it reduces the background in this so-called downward going region, shown in this red arrow here. So before applying our selection criteria, the background is given by the dotted lines, and after applying it, given by the solid lines. And that changes the shape of the background in this angular distribution. So you can see here the data as a function of angle. So we know that most of these events here have been astrophysical neutrinos because the background shape is going downward. So most of this contribution has to be astrophysical, and this downward going shape of the background is related to this correlated cut that we're doing in not allowing events that deposit charge in the outer parts of the detector. And we can measure the spectra using these starting events as well. And the interesting part about this is that we get a different answer. We get about 2.9 spectral index. So, and that's actually going to be interesting because we're going to get different answers depending how we do these measurements. This is a collection of recent measurements that we have done. So here in the horizontal axis is the spectral index. So the smaller the number means there is more high energy neutrinos, and the larger the number means there is less high energy neutrinos. So E2 minus 2 is we call a harder spectrum than the E2 minus 3. And so within error bars, they're all compatible, but we do see certain differences depending how we are doing the selection. So the blue is using these muons through the Earth, and the yellow is using these starting events. And then we see a difference that is quite substantial, and we're trying to understand why that's still the case. Okay. So there is complementarity between the ways which we can discover astrophysical neutrinos. So on one side, we have searches that look for neutrinos of all flavors in all the directions, but are using the outer parts of the detector to block background. And the other side, we use the air to block the backgrounds. And these are good for astronomy and have better angular resolution. Okay, good. So these three methods actually give approximately consistent answers. So here you can see the unfolded neutrino spectrum, artificial neutrino spectrum as a function of energy. You can see the bar in blue is what we obtain with high energy muons, and the crosses are what we obtain with events inside of the detector. And you can see that the more or less they're in agreement, but the starting events in the lower part of the spectrum, they're a little higher than that. That's kind of strange. And we have done newer measurements. So here you have one of our latest measurements. And you can see that when we add data, it still looks a little higher than what you expect from this now shown in pink mu neutrino line. And that brings me to a discussion of what's making these neutrinos, which is the last part of this talk. So we see lots of neutrinos every year, more than 100,000 candidates every year. And we need to find a way to see these neutrino sources. And the way one can do that is by looking for clustering of these neutrinos in this sky map. Okay. So if we look at the highest energy neutrinos, these are shown here. This is the map of all the high neutrinos. You can see that some parts of this map look kind of empty. That emptiness is not because there are no sources of neutrinos, but because the Earth is there. Remember that the Earth actually blocks high energy neutrinos. So that why this direction is Earth going directions. And here the color indicates the energy of your neutrinos. And the different markers are going to indicate if it was true on or restarted in the detector or not. So when one looks at these skies, map of neutrinos, one can look at the highest concentration in the sky. And this is on this 10-year analysis. By the way, this data is now publicly available on the ESCAP website. And the northern hemisphere hotspots is shown here. This northern hemisphere hotspot corresponds to a source, which is NGC1068, which was published in Science a couple of years ago. And it's the brightest neutrino emitter we have ever observed so far. And what you can see here is the data as a function of the angle from the source. And you can see a clear excess of events in the direction of NGC1068. Okay. So we have observed diffuse neutrinos from the static sources, which is this NGC1068. I will show you later that we also see a galactic component. And we can then talk about the connection between PV gamma rays and neutrinos. So if we go back to this slide that I showed you a while back, when we were talking about how these neutrinos are produced at their sources, the neutrinos are produced in collisions of protons with potentially photons. And in that collisions, you produce charged pions and neutral pions. And those are always going to produce neutrinos and gamma rays. And so the question is, if you're looking at these sources, I should also be able to think about the gamma rays that come with these sources. Okay, and as we discussed earlier, not all of these gamma rays can reach us, but some low energy ones should be able to reach our detector. Oops. So if I have a neutrino spectra, here is my cosmic neutrino data on the right, and I assume that my neutrinos and gamma rays are produced in equal amounts. I can then propagate those gamma rays to the universe, and I can compute the number of gamma rays that I should observe at the detector. So what you can see is that there are two lines here. One is this light thinner line in black. That thinner line in black corresponds to this thinner line in red. And then this is thicker line in black. That thicker line in black corresponds to this thicker line in red. So what this is showing you is that if you model the neutrino emission at the sources as this thicker line in black, you produce gamma rays. The gamma rays that are produced with those neutrinos, with the pions, the sibling pions of neutrinos, actually saturate in Fermi gamma ray observations. Okay. Now, what happens if now the neutrino, but you can see there's kind of a problem with this black line is that there's at least one data point at the lower energy that's way too large. So this one here. So now if I increase make my neutrino spectrum steeper, so like I make it like that, for example, so that it now fits that black cross that was not fit before, now the number of gamma rays that I expect to be produced is much higher than the Fermi observation. And this is actually really important. What this is telling you is that the sources of neutrinos have to be sources where the gamma rays are obscured. They are gamma ray obscure sources, because if not, you will be violating these gamma ray observations. Okay, and this is actually now supported by our escape analysis. So this is a newest multi-cascade analysis that also supports the fact that the spectrum tends to be shallower. Okay, so this is a new measurement, for example, that shows you that these low energy data points will correspond to a neutrino flux that will make overshoots the Fermi gamma ray spectrum. And so what does it mean in terms of the spectral index? Essentially, if the neutrino spectral index is softer than about 2.2, then if you model this neutrino spectrum as an unbroken power law, then you are overproducing gamma rays, which implies that the sources of neutrinos, if they had a spectra, are sources that are very thick. Okay. So understanding the neutrino spectra is and the relation to the gamma rays is quite important. So what are these sources? Well, most of Fermi sources are actually blazars. So let's talk about multi-messenger astronomy. So I'm not an astronomer, but blazars or active galactic nuclei are classified by astronomers as different subtypes depending on how the active galaxy is oriented with respect to Earth. So when the active galaxy jet, shown here as this emission, is pointing towards your detector, we call that a blazar. And if you're seeing this active galaxy in other directions, you have different names. Like for example, it could be a safer galaxy if you're looking at that at certain angles, or already quiet and whatnot. So depending on the direction of where you're seeing the object and the properties, the astronomers have different qualifications for these objects. But most of them are active galaxies. So what we try to do is do a multi-method approach to find these objects, where we try to see the neutrinos and the gamma rays in a correlated fashion. And so for that, IceCube has a public alert system where when we see a high neutrino, we automatically release it to LOS, and you can subscribe to these GCN alerts. This is an example of one of those, and you get these little memos that tells you the energy estimation, the direction, on the time of arrival of these events and how it was detected. We read typically, because it's complicated to reconstruct these directions, so I was showing you earlier, it depends on this photon propagation that's expensive. We have a first reconstruction that we update sometime after. So what happens in this so-called real-time system is the DOMs see a hit, they trigger the acquisition system, so 5 seconds. Then there is a processing happens at the pole, and then we message our partners later. We send messages to the University of Wisconsin, and then we follow up with our partners. So it takes about a minute or less than a minute to go from the first initial hits to an alert in the Northern Hemisphere. So this is another example of those. A very famous event alert was this event here, which is IceCube 170922A. This was a 23 TeV muon shown here that was detected in 2017. And the reason this is important is because it actually ends up being one of the events first associated to a neutrino source correlation. So let me show you what that event looked like. So this is how the event looked. So it's coming from the right towards us. Remember these balloons or these circles represent, color represents time, and size represents how much charge it sees. And so this is a muon going from right to left. This is a very well reconstructed horizontal track. And this is a picture of these events. And what was exciting about it is that soon after this event was observed, Fermi looked at the direction of this event and they saw that there was a blazar within 0.1 degrees that was in active, in higher gamma ray activity. And MAGIC saw also emission of high energy gamma rays in that direction. And so this leads to a follow-up cascade of the 2017 events, where IceCube saw it in September, then was seen by multiple observatories after the fact, giving us actually the first multi-messenger observation of a neutrino source. This was published on Science a couple of years ago and led to the first discovery of a neutrino source, which is known as this TXS 0506 plus 056 blazar. So then what we did after we observed this event is IceCube looked at its data to see if there were more events like these ones in the direction of this object. And so we looked at the archival data in the direction of this particular neutrino. And this is, we saw actually that there were actually more events seen by these neutrinos earlier. So what you're seeing here in this top figure is the significance over background of neutrinos in the direction of this source. And in 2017, there is a spike. You see that in orange. But then you can see that there is this larger spike in late 2014, early 2015. That's actually very significant emission. So you may be wondering what's going on here, because we saw this correlation with gamma rays, but then there was this more neutrinos earlier that had no correlation with gamma rays, or at least we didn't send any alerts. And the reason is that there was no gamma ray emission in the earlier times when there was large neutrino emission. And this is actually related to this argument of neutrino opacity. So if you think about neutrino sources as these accelerators, the protons have to have, the source target density has to have a given fixed density for the neutrinos to interact to produce efficiency pions. So when a source is dense enough so that the protons are making efficiently pions and making subsequently decaying into neutrinos, the source is now too dense for gamma rays to interact. So when the source is a little dense, we think that this is some kind of transient source. When the source is a little dense, then it emits a neutrino every now and then. But when it's really dense, it can emit many neutrinos, but now the gamma rays can no longer leave. So this gamma neutrino connection is quite complicated. And actually, we understand this because what's shown here is the opacity of gamma rays and protons in a gamma ray background. So the opacity of protons in a gamma ray background and the gamma ray opacity is related by the ratio of the gamma gamma to p gamma cross sections. Since the gamma cross section is larger than the p gamma cross section, what that makes it is such that when an object is opaque to protons, it's immediately also opaque to gamma rays, making the gammas lose energy at their source. Okay, so this is, so I show this, and you can see this again here. So for example, this is the 3 different visions of this TXS 2014 flare. So the vertical lines that you see here is 2017, and you can see in 2017 there is like 1 neutrino, there's the gamma ray flare, and then there is radio. But when you look at the larger 2014 flare, there is no gamma ray activity. there is something on radio, but nothing on gamma rays. And then we can look at other high neutrino observations. So these are 3 different neutrinos from 3 different objects. And the pink line corresponds to a neutrino arrival time. And the black and blue dots corresponds to gamma ray emission from Fermilab or MAGIC, depending on which plot you're looking at here. And you can see that when the neutrino gets to ice cube, the gamma ray emission seems to be at a low point. So what that's telling you is that the sources are such that the neutrino efficiency and the gamma opacity are anti-correlated, or are correlated in that more neutrino production efficiency is a more opaque gamma source. We also see the same for NGC 1068. Don't bother much about the text here, but if you look at the figure here, the figure shows you the gamma ray neutrino emission. So the green is the neutrino emission from NGC 1068, which is a steady source. And you can see the upper limits from MAGIC and HES that constrain the gamma ray emission from NGC 1068 to not be more than 20 times smaller than neutrino emission, right? So that's because this object is not transparent to gamma ray at those energies, we think. And the final thing I want to say is that we not only have point sources, but recently we have also made improvements in our capacity to reconstruct cascades, in particular to machine learning algorithms, and this is shown here in these figures. And so traditional reconstructions are shown here in gray, and this machine-based learning reconstruction shown in blue. And at high energies, they are better. And with that, we can actually show you for the first time the galaxy neutrinos. And so this is, I think, really cool. So this is the galaxy in various wavelengths, optical and gamma ray and pi knots. And so the last one is the neutrino emission. So this is the first non-electromagnetic picture of our galaxy. And the galactic neutrino emission, it's about 10% of the neutrino emission from all sky. So here you can see on the figure on the right, the neutrino energy in the horizontal axis, and the vertical axis is the intensity of neutrinos from the galaxy, are these colored bars. And this dash bar is the all sky neutrino emission. So you can see it's about 10% of the total sky emission. And here's where I will probably end. I don't think we have time for more. So I just want to thank you for your attention. And these are just some pictures of my group who is working on many of these topics. And I hope that this was entertaining, and we'll do some questions in the next minutes.